I'm going to show you a database design that seems like it could work but is actually not very good. It breaks almost every best practice for database design, and it will cause endless problems for developers, analysts, and anyone who tries to query the data. In this video, I'll walk you through what's wrong with it and then show you how to fix it. I'll also show you a tool that makes it much easier to review your database designs. We're going to look at a bad database design for an online learning platform like Udemy or Coursera. This is a common kind of platform. Students enroll in courses, instructors teach them, and payments are made. We'll start with a messy design, break down why it's bad, and then redesign it properly. If you want to access my SQL Schema Linter tool for validating a database design, check out the link in the description. I'll demo it later in this video. Imagine we've been asked to design the database for an online learning site. It needs to support students and instructors, courses with titles, descriptions and tags, enrollments and payments. This is a pretty common set of requirements. Now let's see the original design for this. Here is the design. We have 5 tables in the database, each with a range of columns. Let's go through it table by table. This is the users table, which captures, I presume, users of the system. We've got students, instructors, and admins all in the same table. There's a type column to indicate what they are. That might sound flexible, but it leads to messiness. Different types of users need different fields, and what happens when we want to store something specific to instructors, like their skills or ratings? Next, we'll look at the course info table. This has a list of courses including the title, details, and the status. There's no link to the user who created the course. We just have the creator's name as a text value. Also, we could assume tags are stored in a single column here, maybe as a comma-separated list. This makes it really hard to filter or join by tag. Next, we have the enrollments table. This stores the courses that the students have enrolled in and what they enrolled. To record this information, instead of using IDs, we're using text. We are capturing the student's email and the course title. That approach breaks referential integrity. If a course title changes, this table won't know. If an email has a typo, the enrollment can't be related to the right student. Let's look at the payments table. We have a few columns: user, course, payment amount, payment date, and method. All of these columns are varchar or free text. This includes payment amount, which is a string, not a number. That means we can't sort or calculate it reliably. Finally, we have the data blob table. This is a mystery table. It could be anything. Without documentation, you and your team will be lost. This is like a strange version of the entity attribute value pattern. It's flexible, but it's hard to maintain. Here's a quick summary of the problems. Mixing different user types in one table with no structure. We're using free text names and emails instead of foreign keys. Storing dates and numbers as strings. No lookup tables for things like status or payment methods. The tag handling is denormalized. Finally, a generic data blob table with no clear purpose. This design will make querying painful and maintaining the system nearly impossible as it grows. So let's clean it up. Now let me show you a better version. This design uses proper data types, relationships, and lookup tables, and it's way more scalable. We've split the users table into 2 tables, one for each type of user. We'll start with the student table. We've added primary keys to all tables, including this table. Most of the other columns are the same, but we've removed the role table as we have indicated the roles by using 2 different tables. Date of birth and registration date are now proper date and date time data types. The instructor table is the other table split from users. It's similar to students for now, but it relates to different tables in different ways. The data types are updated as well. We could have kept these as a single users table with a role table as a lookup table, so if you prefer that approach, you could do that. The course table has been updated slightly. You might notice all of the table names have been slightly renamed to use singular names rather than plural, so course instead of courses. This is a personal preference, so if you prefer a plural name, you can use those instead. We reference the instructor using instructor ID, which is a foreign key to the instructor table. Now the link is clear and safe. The course status has been captured using a separate lookup table. In the status value column, we could have values like draft, completed, or archived. This links to the course table using the status ID column here. Next, we can look at the concept of tags. Instead of having the tags for a course in a single column, we split the tags into a proper many-to-many relationship. We have a table called tag, which has an ID and a name. The name is the value of the tag, such as design or communication or popular or bestseller. The course tag table stores the tags for each course. A course can have many tags and a tag can have many courses, so we need this joining table. Now you can query for all courses with a specific tag or all tags for a course, and the queries are clean. Here is our enrollment table. It stores a record of students who enroll or join courses just like the original design. However, it has been improved. We have added foreign keys to both the student and course tables to refer to the related records instead of text fields. Also, the status column can now reference this enrollment status lookup table. This works in a similar way to the course status. We can easily filter on this status and change the status of an enrollment. Our last tables are the payment and payment method tables. We've linked the payment to the student and course tables, just like with enrollments. This uses a foreign key, so it's more reliable than just text values. We've used a lookup table for the payment method. We've also used better data types for the columns, such as number types for the payment amount and date time for the payment date. All of that review work and schema updates were done manually. What if there was a way to do it much faster? I've built this AI-based tool called the SQL Schema Linter. It allows you to paste in a series of create table statements for your database and analyze the design for a range of good practices. I'll paste in the create table statements for the original design and click Analyze. After a few moments, a list of suggestions is shown. It reveals many of the same things we discovered in this video and perhaps a few more. There's also an updated create table statement for each table that was analysed. You can use this SQL instead, or you can review the changes and make it the changes that you want. It's up to you. If you want to use this free tool, check out the link in the description. Here are a few lessons from this redesign. Always use foreign keys for relationships, not text values. Choose the right data types. Use date, date time, decimal, not varchar for everything. Normalize repeating or multi-value data like tags or payment methods. Avoid catch-all tables like data blob. They're flexible but extremely hard to work with. Split your concerns. If different user types need different fields, consider separate tables or polymorphic patterns. We did this in our design by splitting users into instructor and student. A good design helps the whole team, developers, analysts, testers, and even future you. If you want to get better at designing databases from real-world requirements, check out my Effective Database Design course. It walks you through how to go from idea to clean schema, using practical examples just like this one. There's a link in the description. Sometimes you'll want to see an example of a good design and why it works. You'll want to watch this video next, where I demonstrate how I would design a database for Spotify, the music streaming platform. Thanks for watching.